Hi, ladies and gentlemen. Welcome to the last section for Chapter 2. We're going to finish up talking about square matrices and row reduction, the whole idea of Gaussian elimination, Gauss-Jordan elimination, with the conversation associated with permutations. And taking a look here, we're going to talk about permutations and associated transposes. So permutations are where we are going to actually permute or swap rows or columns. Generally, of course, when we're doing Gaussian elimination, we are swapping rows. We are moving out zero pivots in order to be able to conduct our elimination to come up with solutions to a system. So let's just take a quick look at the highlights here. We'll talk a little bit about the fact that there are n factorial permutations. For those of you who have not taken probability or statistics yet, this whole idea of permutations is pretty important. One key fact about permutation matrices, the transpose is equal to the inverse, and we'll talk about transposes momentarily. One of the big results for transposes has to do with taking the transpose of a matrix vector product or a matrix product. And that's all outlined in the transpose section. And then finally, we'll talk about symmetric matrices, which are fundamental for where we're headed to do singular value decomposition. First things first, all of the permutations are, what we do is we take the identity matrix and we do the permutation that we want, and then we apply that permutation matrix. So let me tell you what I mean. So we're going to start with the identity matrix, something that looks like this. And what we're going to do is we're going to take the product and we'll just pick our standard matrix that looks like this. And what I want to do is I want to swap the first and second rows. And so what I'm going to do is I'm going to come in here and I'm going to swap the first and second rows of the identity matrix. So I'm going to put the second row there and the first row here. And now, as we do the multiplication, it's really easy to see what's happening. That first row, this first row here, as we sweep through the rows of the matrix on the right, we can see that we're going to pick up that second row. We're going to have 4, 5, 6. That's going to be the first row in our product. And then it's easy to see that the second row of the output is going to, as we sweep through, be the first row of the matrix on the right, which is 1, 2, 3, 7, 8, 9. And so that's all there is to it. That's all we really have to do. And it turns out that building the elimination matrices was the same way. Remember, we said when we built elimination matrices in general, we start with the identity matrix. So we would have a matrix that looked like this, and then if we wanted to do elimination of the third equation or third row using the first variable, we would come in and we would make a modification here, which is why we have negative L31. And that's the whole idea behind elimination matrices. So a lot of these things start with the identity matrix, and then we do our operations from there. So he provides some examples and conversation here about even and odd. So there are even permutations and odd permutations. And that's left for you to read. You can take a look through those things. A really important result is the fact that if we have a permutation matrix, the inverse of a permutation matrix is equal to the transpose of the permutation matrix. Let's go back and take a look at what that means here. So transpose, and we'll talk more about this. Most of you are familiar with this idea, and there's a big chunk of section 2.4 dedicated to this conversation, but transpose is just going to be taking the rows and the columns of a matrix and flipping them. So we're going to take the things that are the rows, and those are going to become the columns, and hence the things that are the columns are going to become the rows. So let me write this in yellow. So the first row that I have circled here in yellow is going to become the first column. So P transpose is 0, 1, 0. And then the second row is going to be equal to the second column of the transpose. And then the third row becomes the third column. And this is P transpose if the cyan matrix is P. And in this case, we end up with the same matrix. But in all cases, this is equal to the inverse. It's going to undo the operation that the permutation matrix did. That's what inverses do, right? They reverse the operation of what the original matrix has already done. Well, since we swapped the first and second rows, then all that's going to happen in the inverse is we're going to swap them back. So it makes perfect sense that it's exactly the same matrix. But that's a really important property for permutation matrices. Let's talk about some more of the properties of permutation matrices. All of these are important. Most of them are reasonably straightforward, not a big surprise. So the ones that occur in a permutation matrix are all going to occur in different rows and different columns, which is obvious from the standpoint that we started with the identity matrix and all we did was swap the rows or swap the columns of the identity matrix. So of course there's 1, 1 in each row and each column. Another thing that's important about permutation matrices is that they are orthogonal matrices. So we are not going to introduce the term technically until chapter 4. But an orthogonal matrix is a matrix whose columns are mutually orthogonal. Every column is orthogonal to every other column. Obviously, the identity matrix is that way, but every permutation matrix is also that way. And again, this is pretty straightforward to see. If we start with an orthogonal matrix and all we do is swap the columns around or swap the rows around, then we would expect the matrix to continue to be orthogonal, and it is. The next result is less obvious. The product of two permutation matrices is a permutation, and the inverse is a permutation matrix as well. So the inverse we believe, right, because remember an important result, the inverse of the permutation matrix is just the transpose. So it would make sense that if what we were doing was swapping rows or columns, if we take a transpose, we're still swapping rows and columns. The product is a little bit different, and you can work through that, think about it a little bit, but it's a true statement. The product of two permutation matrices is going to be another permutation matrix. And that flows into our big result right here for LU decomposition. So what he says in this statement is all the permutations required in order for us to be able to do Gaussian elimination, all of those permutations can be rolled up into a single permutation matrix. So what we are able to do is we are able to take PA equals LU, and let me orient you. The P matrix is the permutation matrix. It contains all the permutations that were necessary for us to be able to complete our Gaussian elimination and come up with the LU decomposition. We roll those all in and we can left multiply onto A. That will do all the permutations up front that we need to do such that as we conduct our Gaussian elimination, we won't run into any issues with zero pivots. So this is very much the way all software programs do LU decomposition. They take and apply permutations, and we'll talk about why they do that in just a moment. So he provides some examples here. You should definitely look through the examples. Here's the real issue that we're concerned about. What happens when we hit a zero pivot? So when we hit a zero pivot, we have to swap rows in order to move that zero pivot out. If we can't do that, if the pivot is 0 and all the values below the pivot are equal to 0, then we have a singular matrix. Remember the conversation we were having in section 2.1. That singular matrix is not going to be invertible. There's no way for us to put a non-zero pivot in order to do elimination. Barring that, we can do a row swap to get a non-zero value in. And that is this whole idea associated with permuting the rows of our matrix. And again, he works through a nice example here. You want to read through and make sure that you understand all of this example. So that moves us to the whole concept of partial pivoting. Partial pivoting is something that, again, pretty much all software programs use partial pivoting, and it's to avoid cancellation error. So what I want to do is I want to just orient you to what cancellation error is, because this is one of the more important topics from numerical analysis, and I know a lot of you are not going to have the opportunity to take a numerical analysis course, but it's important to understand what cancellation error is and how it affects what we can do with our computation within a computer. So all I'm going to do is I'm going to take a look at the derivative for f of x is cosine of x. So you know that we approximate the derivative. So f prime of x is approximately, and I'm just going to use a forward difference. It's f at x plus delta x minus f of x divided by delta x. And this gives us, at whatever our x value happens to be, an approximation. And so what you were told in calculus class is, if you want a more accurate approximation, you end up using smaller and smaller and smaller delta x's, right? The whole concept of what's going on here is we have a cosine function that's going like this. We're going to approximate out here at 1.5, and what we want to do is approximate the slope out here. So we're going to approximate this slope, and we're going to do it by taking the 1.5 plus a step forward, and we're going to look at the difference in the function values and divide by the length of our step. And we know that that derivative is going to be close to 1, but what we want to do is look at how does this change as we take the delta x and shrink it down. Because again, we all think that it's going to become more and more and more accurate. Let me show you the reality of what happens. This shows the result of step size. So this is the delta x as we shrink it down. And this is the relative error of the derivative versus the actual value, which is easy for us to calculate as the negative sign value. And things behave, although it's a little bit wonky up here in the beginning, right? This doesn't necessarily follow with what we think, but it's generally, this trend is correct. As the step size is getting smaller, we're moving to the left here, as the step size is getting smaller, the relative error is going down. And that continues to work using the forward difference until we reach step sizes smaller than 10 to the minus 8. When the step size becomes even smaller, we are dividing by smaller and smaller and smaller numbers. And division by small numbers is cancellation error. It causes error because we are amplifying, by dividing by a small number, we are amplifying errors in the numerator. And that's exactly what we see here. We end up with continuing to smaller and smaller step sizes. Our relative error actually increases. Our approximation of the derivative is worse, and it gets worse and worse the smaller and smaller steps we take. This is counter to what most of you have been told. I just need you to understand that this is the reality of what happens with cancellation error. Because of that, we do something called partial pivoting. And what partial pivoting comes down to, and he has a great example that you need to walk through here. We're going to start by eliminating in the first column as we normally do. What we've been doing this entire time is we have been using 1 as our pivot, and we've been eliminating on the way down. Well, that means we're dividing by that 1 value in order to eliminate the 2 and the 3. The most stable approach to this is to actually take the 3, and that's what he does with this permutation matrix. He takes the 3 and he puts it up there. He takes the largest value in each column that's going to be used for elimination, and he puts that in as the pivot. That's partial pivoting. We do that because it significantly increases the numerical stability for calculating the Gaussian elimination. And you can read through this. You can see what he does with respect to this swap. When we talk about the largest number, we mean magnitude. So sign has nothing to do with this. Whether we're dividing by a positive or negative number has no effect on cancellation error. We just want to divide by the largest numbers possible. So, and we'll have this associated with project, and so we'll have a greater understanding of this once we actually program it up. So the next thing to talk about is permutations on the left and the right. So something that we've been talking about, but we haven't emphasized, is the fact that because multiplication is not commutative, right? So in general, two matrices, when we take A times B and B times A, we don't end up with the same thing. And what this means is we have left multiplication and we have right multiplication. So when we have a matrix A and we want to multiply by a permutation matrix, we could multiply on the left-hand side, or we could multiply on the right-hand side. And that's how we refer to them: left multiplication, right multiplication. In the case of permutation matrices, left multiplication, and if we think about what this is, let's go back to our previous example where we are swapping the first and second rows. We've permuted the rows of the identity matrix, and because we're on the left, the rows are on the left, and we're permuting rows. If, however, we have the permutation matrix on the right-hand side, we now are grabbing the columns of the permutation matrix and we're sweeping through the columns of A. This is going to give us column swaps. So here we are permuting the columns. Sorry, a little exuberant on the U there. We are permuting the columns. We're doing column swaps. And so that's what he's referencing when he talks about taking a look at what he calls PAQ. Both P and Q for him are permutation matrices. Multiplication on the left is swapping rows. Multiplication on the right by Q is swapping columns. And that's the conversation that he's having through here. Take a look at those examples. The next topic for today is transpose. You're just going to read through all of the transpose information. Most of you are familiar with what transpose is. I've already demonstrated for you how we take a matrix and we think about its rows, and those rows become the columns of the transpose. And he has examples and runs through all of this. Of particular note are the results that are inside of the box here. The sum and the product and the inverse as it relates to transposes. All of these results he goes on to explain throughout the rest of this subsection, and you need to read through this and make sure you're familiar with this entire conversation about transposes of products, sums, and transpose with respect to the inverse. So that continues all the way down here to the meaning of inner products. So that's the next topic. As I said, section 2.4 is filled with a lot of material. In here, he's talking about inner products and outer products. This is review for us. We've already talked about this. Dot products are inner products, and then the outer products are the rank 1 matrices. So recall, if I have x dot y, two vectors, I can rewrite that, and I think always of vectors as columns. I can rewrite that as x vector transpose times y vector, which graphically looks like this. I have the x vector and I have the y vector, and when I take these two vectors, I'm going to end up with a 1 by 1, which is a scalar. I'm just going to end up with a number when I do this. The outer products are where I take x vector times y vector transpose. So this looks like the x vector. Vectors are always columns. I have my x vector, and then I have the vector y, and this is the y vector, and I've transposed it to make it into a row. And the result of this is a matrix, and it's a rank 1 matrix. So we've looked at these before. This is just an opportunity for you to look at some examples that he cited, as well as just refresh yourself a little bit on this idea. So all of this conversation, he does start to get into some of the ideas associated with solving, for example, ax equals 0, and solving a related problem, which would be y vector times A transpose equals 0, where I'm now looking for the linear combinations of the rows of A transpose, which are the columns of A, and that's the same thing that this is doing. X is looking at the linear combinations of the columns of A, and in this case, Y is looking at the linear combinations of the rows of A transpose, but the rows of A transpose are the columns of A. So these two problems are related to one another. And in fact, we're solving for the same type of thing. So that's this conversation that he's having in here. And he's also looking at different ways to write dot products. One thing that I want to point out is the idea of inner product. So when we're talking about function spaces, and we haven't spent much time talking about this, we will over the next couple of weeks. Imagine for a minute polynomials, and you can think about quadratic polynomials. So the set of quadratic polynomials is the span, all possible linear combinations of 1x and x squared. And we'll talk more about this. I'm just giving you a little bit of an idea, because what's important here is to realize when we talk about dot product in the functions, we really are talking about an inner product. So we can easily see that every quadratic polynomial is a linear combination of these functions. We're accustomed to that. We've seen that for a lot of years. There's a way in which we define dot product when we're talking about functions, and it's really an inner product. And he's talking about it here. The fact that his inner product goes negative infinity to infinity, that is the result of the types of functions he's talking about. Negative infinity to infinity would not work for polynomials because a lot of those integrals would not have solutions. They would not exist. So, but he's talking in general, negative infinity to infinity. For polynomials, we generally talk about negative 1 to 1 as our limits of integration for our inner product. And then he has a couple of functions, right? So he talks about function x and function y, and it's a little bit unfortunate because he's using the same notation as he did for the vectors. What I'm going to do is the more standard notation that you will see in different books, which is f and g. So these are literally functions, and we have defined what's called an inner product. And what I'm going to do is just briefly show you that this is the same type of idea as a product, a dot product in the Rn vector spaces. So the polynomials, you can imagine for a minute we have two polynomials. Let me call them P1 and P2. So these are two different polynomials, and it's the same type of thing. This could be the definition of an inner product for polynomials. So the inner product, think for a minute about what a dot product is. If I take the dot product of x and y, I am going to take the product of all of the components that match up for my x and y vectors, and I'm going to just sum them together. This is what a dot product is. You're familiar with this. Now let's take a look at what's happening here. I am taking the two functions, and at every value of t, I am considering their product. It's exactly the same as what we're doing at each of these, except we have, instead of a finite number of values, a finite number of components inside of our vector. That's what happens when we have vectors from the real numbers. What we have instead is we have an infinite number of these things. And so this is multiplying the two functions, the two vectors, which are functions, at each value across their domain. Then what do? Well, the next thing we do is we add up all of those products. That's what a dot product is. And what's an integral? It's just a summation sign. It's just adding up all of these products that we've determined. So the inner products and the dot products are the same type of thing. The inner products apply when we have function spaces. The dot products apply when we have Rn vector spaces, right? So we have vectors here that come from some space of real numbers. Then, and you can read through this. This is just more of an interesting item here about the application of the derivative matrix, and we'll talk more about that. So the last topic that we have has to do with symmetric matrices. You're familiar already with the definition of a symmetric matrix. Symmetric matrix is where we have some item that's equal to its transpose. And what we have when we do the LU decomposition for a symmetric matrix, right? So we've talked A is equal to LU. If I have a symmetric matrix S, it's also something that I can do LU decomposition on, probably. But there's a slight adjustment. It turns out that because this matrix is symmetric, the L matrix is what it is, but the upper triangular matrix can be written as a product of a diagonal matrix, a matrix that has non-zero values only along the main diagonal, multiplied times L transpose. And that's what gives me my upper triangular matrix. So this leads us to what's called a Cholesky decomposition, and we'll talk a little bit more about that. But it's important to realize that as we have symmetric matrices, we're beginning to build some structure into what's happening. Let me show you in MATLAB. So I have an A matrix here where I have found the L and U decomposition. And you'll notice this matrix is symmetric, right? So I've got my main diagonal here, and then across the main diagonal, these values match up. And that's going to give me a symmetric matrix. And we could even see, right, if I take A transpose, of course I get the same matrix as I had up here for A. Now the question is, what is this L times D times L transpose? Let me introduce you to another function in MATLAB. What I'm going to do is just call this DUM, and this is the diagonal of U. So that diag command actually does two things for us. If I feed it a square matrix, it will pull off the values that are on the main diagonal as a vector. And that's what I'm going to do here. Okay. If I feed it a vector, so I'm going to say D is equal to diag of DUM. If I feed it a vector, it's going to build a square matrix with this vector along the main diagonal. So it's a dual use function. Give it a matrix, it gives you the main diagonal. Give it a vector, it gives you a matrix with that vector as the main diagonal. And so now what I want to do is I want to take a look at L and D and L transpose. So the L transpose is just the transpose of the matrix we have up here. And let's just look at their products. So we have L times D times L transpose. And it gives us this, and we will remind ourselves of what A is, and it's equal to the same thing. This result always holds when we have a symmetric matrix where we can do the LU decomposition. And he just walks through and has that conversation in here. The last conversation has to do with an example where we use symmetric matrices, and also a little bit about block factorization, which is not really something that we're going to talk about. At the very end, and I recommend you do this for every chapter, he provides a summary. Some of the things that are important and kind of a step back and a bigger look at what's happened inside of this chapter. So this chapter 2 summary is quite valuable, and I highly recommend that you take a look through it. The only other topic I wanted to discuss with you is permutations, because I know some of you have yet to take a probability and statistics class. So there's a function in MATLAB called perms, and when you feed it a set of numbers, it will give you the permutations for that set of numbers. So in this case, we've done the permutations of 1 and 2, which is 1, 2 or 2, 1. permutations of 1, 2, and 3, and it shows us all 6 combinations of the way in which we can write 1, 2, and 3. Let's do another one. 1, 2, 3, 4, and this is all 24 combinations. So this is demonstrating the whole idea of the factorial. If we do 4 factorial in MATLAB, it tells us how many combinations we have. This is one of Strang's big points throughout section 2.4. He talks about the number of permutations that we can make with the identity matrix. And you're familiar, most of you, with the rate at which factorial increases. Take, for example, the permutations 1 through 7. And here we have thousands upon thousands upon thousands of different permutations for 1 through 7. How many? That's easy enough for us to do. Up arrow, factorial 7, we have 5,000. All right, that's the end of the content. Let's take a look at our questions for today. So we have 3 items here. Permutation matrix, the whole concept of partial pivoting, explain what's going on and why we care. And then here is generating a symmetric matrix and taking a look at its column space and doing some calculations with the symmetric matrix. We look forward to seeing you in class. Thanks.